In Part 3 of Lecture 6, we will discuss semaphores. Edsger Dijkstra was a Dutch-born computer scientist who was particularly interested in synchronization problems and proposed a solution based loosely on railroad flags. The main difference is that in his case, a semaphore wasn't a red or green flag, but an integer value that is not allowed to become negative. His semaphores could only be manipulated by the two primitives p for proberen, Dutch for test, the wait operator, and v for verhogen, Dutch for increment, the signal operator. V of s was simply a matter of incrementing the semaphore, but p of s involved waiting as long as the semaphore was 0, and then incrementing it. This meant that if a process found the semaphore with a value of 0, it would wait until it was 1, and then it would reset it to 0. This is how the wait and signal operators are implemented. The nicest part of using semaphores is the fact that the operations are indivisible and they don't require all the code around them that we have seen before. Providing mutual exclusion around a critical section means simply placing a p operator before and a v operator after a critical section, with the appropriate semaphore variable for this particular critical section. Let's take a look at how one would implement a semaphore in C++. There are three public methods: a constructor and the p and v operators. There is only one private item, the value of the semaphore itself. Since the semaphore can be used to control the use of any finite resource, including buffer blocks, ports, terminals, as well as providing mutual exclusion on critical sections, we can set it initially to whatever integer value is appropriate in this case. Because p and v must be indivisible, we must disable interrupts when entering and enable them again as we exit. In between, we simply busy wait until the value is non-zero, enabling and disabling interrupts so the operating system can do whatever other work it has to do. V, as we would expect, is simpler than P, with an increment statement between the disabling and enabling of interrupts. Let's take another look at the consumer-producer problem. We have n buffers to work with. These will relate to the semaphores full and empty, which tell us how many full and empty buffers there are, respectively. We will also need the semaphore mutex for mutual exclusion, which will guarantee mutual exclusion of critical sections for us. In our producer process, we first produce an item, whatever that might be. Then we need to get a buffer to fill. Since allocating a buffer is a critical section, we protect it with our mutex or mutual exclusion semaphore. We do not want the consumer in here until after we're finished. Once we have the buffer allocated, we increment the mutex semaphore. After we copy the item into the formerly empty buffer, we want to release the buffer. So this is also a critical section that requires the use of the mutual exclusion semaphore. Once we finish this step, not only do we increment the mutual exclusion semaphore to signal availability of the buffer pool for manipulation, but we signal that there is another full buffer if the consumer is waiting for it. The consumer does something analogous to this. it has to wait for there to be an available full buffer, hence the P of full statement. Then it enters the critical section, obtains a buffer, and copies from it. Notice that the statement here equals obtain full is protected by the mutual exclusion semaphore. After that, we release the now empty buffer, protecting the statement with the use of the mutex semaphore. Lastly, we signal the availability of the empty buffer and consume the item. The reader-writer problem is based on a concept that you would expect to find commonly in a concurrent system. You have processes that are looking to read and write in the same file or on the same record. The problem is a lot like the checkbook manager that we spoke about much earlier. What we're looking to do is to ensure that the information in the file is accurate and up to date. To do this, we have to enforce two conditions. When a process has started reading, no writers can begin. When a process has started writing, no other process can read or write. The real problem is to avoid starving readers by always giving writers precedence, and to avoid starving writers by making sure that they wait for all the readers to finish. The simplest solution that avoids this is to have the reader come in, reserve the resource, write, and then free the resource. To avoid the potential starvation, we queue up exactly one reader and the writer's queue. We use the mutex semaphore to protect the critical section, where we increment the count, and then if the count of readers is 1, we use the P operation on the writer's semaphore to enqueue this reader with the writers. In the other critical section, we do the reverse when finishing. This prevents starvation of readers and writers. The dining philosopher's problem is another classic problem of concurrency. We imagine that there are 5 philosophers who have gone out for a meal in a Chinese restaurant, and they are planning to eat with chopsticks. They each sit and think for a while, and when they are finished thinking, they pick up a chopstick on either side and start to eat. But there is a problem. There is only one chopstick on either side, and it may have been taken by the philosopher sitting next to him or her if he or she finished thinking first. The simplest solution is to have 5 semaphores, one for each chopstick, each of which is a mutual exclusion semaphore initialized to 1. As each philosopher gets ready to eat, he or she reserves, and if necessary waits for, the chopstick on either side, eats, and then frees both of them. The only problem is that the method of holding onto a resource which belongs exclusively to one entity, and then waiting for another, sets up the very real possibility of a deadlock. It is possible that the 5 philosophers could each be holding a left chopstick, waiting for a right one forever. Clearly, we need to do something to break up the potential deadlock. Let's consider a few possible solutions. One solution is to limit ourselves to 4 philosophers dining together. With 5 chopsticks, there will always be one who can start eating. One possibility is to require a philosopher to pick up both chopsticks at once. If only one of the 2 chopsticks on either side is available, we may have him or her wait. The only problem is that this may lead to starving a philosopher. The last possibility is to have a philosopher pick up his or her chopstick in a different order from everyone else, or to have philosophers on either side first pick up that same chopstick. Only if that chopstick is free do they look to see if the other chopstick is available. as we will see later, we have tried to eliminate 3 of the 4 conditions necessary for deadlock. Once these have been made impossible, deadlock cannot happen.